Hello students, in this video we'll see an application of the complement probability rule in a classical example called the birthday problem. So the birthday problem asks the following. In a room with n capital people, what is the probability that at least two of them have the same birthday? And in this problem, we'll assume that there are no leap years, assuming no leap years. So February 29th is excluded in this problem. And so let's think about this. So at first it may seem like it's a rather difficult problem, but what we'll do instead is we're going to construct a sample space. So our sample space will be the set of all pairs x1, x2, x3, all the way up to xn, capital. And with these x1, x2, x3, xn, capital, is they'll represent the number corresponding to the birthday. So January 1st would be 1. So if we let January 1st equal 1, January 2nd equal 2, all the way up to, and January is 31 days, so there are 31 days in January, so then February 1 would be 32, etc., all the way down to December 31st, which would be 365. So we're going to number all the dates in the year according to this rule. And then x1 will be the number that corresponds to the birthday of the first person, x2 is the number that corresponds to the birthday of the second person, x3 the third person, and xn it corresponds to the number of the birthday of the nth person. And all of these xi, so such that xi is between 1 and 365 for each I in 1, 2, all the way up to n capital. And so we can actually compute the size of our sample space. So the size of our sample space, well, there are 365 choices for the first slot. There are 365 for the second, 365 for the third, 365 for the nth slot, and so I have n copies of 365. So this is 365 to the power n. So the sample space is rather large if n is large. So now what we'll do is our problem is to find the probability that at least two of them have the same birthday. Let's look at a different problem. So I'm going to look at the complement of this. So the complement of our event is that no two people have the same birthday. That means of all of these n people, they all have different birthdays. If they all have different birthdays, that means x1, x2, x3, all the way up to xn correspond to different numbers. So let's see what happens. So to compute this probability, so let's call this event, let's call this a complement, and we're going to try to find the probability of A. So what would the probability of A complement be? The probability of A complement would be, well, the denominator is the total number of possible outcomes, 365 to the n capital. And then let's think about this. So how many choices are there for x1? Well, there are 365 choices for x1. How many choices for x2? There are 364, because you can't use one of the ones you chose for x1. Then 363 for x3. And there are n, so we'll have 365 minus n. But if n was equal to 2, I would need a 4 So we need to add a +1 here to get the number right. So this is the probability of A complement. So what we do now to find the probability of A is we subtract this from 1. So the probability of A, this implies the probability of A is 1 minus 365, 364, all the way up to 365 minus n plus 1. All these things are multiplied. All divided by 365 to the power n. And as it turns out, if you want the probability to be over, if you want this probability of A to be over 1/2, you need to only choose n to be around the order of between 20 and 30. So it's only required to have about between 20 and 30 people, and you can actually compute this numerically to figure out that if you want 2 people in the same room to have the same birthday, you only need about on the order of 30 people. You don't need half the population. So there's actually a really small value of n for which this probability exceeds 1/2. So yet again, we see the probability of finding we find the advantage of using the probability of a complement to find the probability of an event. Thank you very much.